All right, so today
All right.
Richard is going to give a lecture for the group. The title is Light and Atoms Seminar Series. So it's the first of a series of 3 seminars, correct, Richard? That will be given every consecutive Wednesday from now on today and the Wednesday after and one Wednesday after. So Richard, whenever you want, floor is yours.
All right. So welcome, first of all. And I would like to talk about, in this seminar/lecture series, about light and atoms, or maybe if you want, the question of how light and atoms interact with. And so this will be a quite fundamental series. So we start really from the basics, or we want to at least understand many of the basics that can be easily glossed over. And in particular, since this will be topics that many of us studied already in undergrad, but perhaps certain approximations, certain assumptions are not always clear or are not necessarily always questioned, or certain aspects are just not discussed. So the hope is that it will become a bit more clearer after this lecture series, seminar series. Okay, so first of all, the motivation behind this is, of course, that electromagnetism is fundamental in our description of the universe, is all around us in experiments and also in theoretical physics. And it is also a very simple theory. However, it is also a gauge theory. And so this very simple gauge theory has a lot of subtleties that are characteristic of gauge theories in general. And understanding electromagnetism, therefore, is a first step to understand more complicated theories. And questions that are related to this are then, so what are the dynamical degrees of freedom? How do we handle constraints, in particular related to gauge degrees of freedom? And because we have this freedom in our theory, so how and which should we choose a representation? So many different ways. For instance, we can work with a minimal coupling Hamiltonian, we work with a multipolar expansion. And lastly, what are the assumptions that go into these different models and into the derivation of these models? And these are the overarching questions here. Now, in particular, what we want to discuss here is, so we start, as I said, very basic, with the quantization of electromagnetism, in particular in the Coulomb gauge. And that will then allow us to go from there to different representations that are in particular often equivalent in just a different form, with working with different degrees of freedom, different representations. And this will be also a topic of the next Wednesday then. The bulk of next Wednesday will be then about the multipolar Hamiltonians, in particular dipolar expansion, and also when we consider all atomic degrees of freedom to be quantum. And that is, of course, something that is not so commonly done, but it has some very interesting phenomenological implications that are worth discussing. And then at the last seminar in 2 weeks, we want to then discuss the relativistic formulation of quantum electrodynamics and how it then reduces in the low energy limit to what we have discussed so far previously, so today and next week. And in particular, so for today, again, we want to start really with the basics. So that means reviewing classical electromagnetism. We want to then quantize in the Coulomb gauge, and then we are in the position to understand how can we express different representations of the theory with different degrees of freedom. And here will largely follow for this lecture today, for this seminar today, the book by Cohen Tanucci. Okay, yeah, and so if you have any questions, please just let me know, because it's really about getting to understand what not always is discussed in great detail, or when we are working with that in our research on our own. We not necessarily start from the basics, but we take a stepping stone further on. Okay, so classical electromagnetism. So let's start with the classical Maxwell equation, of course. we all probably know about this. So we have the electric field and magnetic field, and we have dynamic equations that in particular take into account charge currents and charge densities. So currents and densities that are created by matter. And then with the Gauss law and also the last Maxwell equation, we can derive the continuity equation. And this just tells us that we have charge conservation. So rho again is the charge density and J is the charge current. Okay, and how do we now model matter in this context? Usually is that we assume point particles. So if we have a set of point particles, we can define the density that is associated with each point particle by a delta function and the corresponding charge. And similarly then for the charge current, we have the localization with the corresponding velocity vector and the charge. And then we also know how forces act on these charged particles by the Lorentz force. That is dependent on the electric field and the magnetic field. And knowing Maxwell's equation, knowing the Lorentz force, we then have for our system of field, so electromagnetic fields and the particles, all that we need to know in order to fully determine its dynamical evolution. So if you know at the time t0, the electric field configuration, the magnetic field configuration, the initial position of the particles and the initial velocity of the particles, then we can just determine how the system of particles and field is going to evolve. All right. Of course, what is also often done is that we define potentials that replace our electric and magnetic field. So in particular, the vector potential and the scalar potential U. And if we plug this in the Maxwell equations, then automatically, just by construction, two of these Maxwell equations are automatically satisfied. And this is because the divergence of the curl of a vector field is 0, and also that the curl of a gradient of a scalar field is 0. So this does not give us anything new. What is new is, however, is two new equations of motions in terms of the vector and scalar potential. Okay, so first of all, or importantly, what I want to stress here is that equation 11, so the first equation, has no time derivative for U, for the scalar potential. And that means, and that is what we will see also later on in much more detail in different contexts, is that the scalar potential is not a dynamical degree of freedom, it's not dynamical variable. And therefore, it's in particular in relation to the Coulomb gauge quantization, it will be very helpful to just express the scalar field in terms of all the other degrees of freedom, and therefore we can eliminate it. But later more about that. But so before we go there, let us observe the gauge degrees of the gauge freedom that we have in this theory now. So for every replacement of the old scalar potential, the old vector potential, of course, we can define new scalar potential, new vector potential. If you do the substitution, the equation of motions will not be changed for that. And again, so there are different choices we can make. We can go to the Coulomb gauge. That is what we will focus on today, where we have that the divergence of A is 0, but there are other well-justified gauge choices as well. So the Poincaré gauge is where we have the Fourier or the Fourier version of that, basically that that R dot A is 0. And then last lecture, we will also discuss the Lorentz gauge in more detail, which is about manifest covariance. All right. So before we quantize in the Coulomb gauge, however, we want to do something else. We want to decompose our vector fields in terms of longitudinal and transverse components, so that we define it in this form, V parallel and V perpendicular. And we define each of these components by the following relation. So if we go into Fourier space, then we say that the parallel component of the vector field V has to satisfy this relation. So it tells us that we are parallel to the propagating wave components of the field, where k is the wave vector components of the field in Fourier, if you go to Fourier space, of course. And similarly, a perpendicular component of the vector field cannot have an overlap with the wave vector components, and therefore it's orthogonal to the propagation direction if you want. Now, of course, this decomposition is not Lorentz invariant, and it will be also not very important in this lecture about that is not Lorentz invariant. What is more is that it introduces non-local effects. So if we do this, and we will see that in a little bit, is that the electric field will get non-local terms in the perpendicular and in the longitudinal components that, of course, will cancel each other out. So it seems a bit artificial. And why do we do this? The simple reason is that it simplifies Maxwell's equations tremendously and will allow us to a very good approximation for a very non-relativistic particle motion to have a very easy process of defining our degrees of freedom in this theory. We will see that in more detail in a little bit, but just as a heads up. So now what we can also do is, now that we have done this decomposition and we go to the Fourier space of our Maxwell's equation, so it's equivalent just in after Fourier transformation, then we know from Gauss' law and the relation for the magnetic field, we see then immediately, just by definition, that the magnetic field has no parallel components to the wave vector. It's therefore a transverse field, and that the electric field is a transverse field unless we have charges present in our system. And therefore, if you have charges present, then there is always a longitudinal component. If you now go back to real space, so inverse Fourier transform, then this seems very familiar. This expression is just the electric field that is generated by the Coulomb potential of all charges present. And so again, let me go back to what I said earlier. Now the parallel component of the electric field is instantaneous. It is the Coulomb potential. And from a relativistic point of view, that seems very non-physical, but one can show that the transverse component of the electric field has also an instantaneous component that exactly cancels out the parallel component of that. And in particular, this is non-malicious if one realizes that only the total electric field has a physical meaning and not just one component of that. If we write now the electric field in terms of the vector potential and the scalar potential, we can also see what it means in terms of those. So the parallel component is the parallel component of the vector potential and also the gradient on U. The perpendicular component, however, has no such contribution just by definition of the perpendicular component, and therefore it is only dependent on the transverse component of the vector potential, and therefore it is also gauge invariant. So if you do a gauge transformation, then only the longitudinal components will change. In particular, if we choose the Coulomb gauge, so remember that was the divergence of A is 0, or if we go into express this in terms of the different components, it's just the definition of that the longitudinal component is 0, and that means that the longitudinal component of the electric field is just the gradient of the scalar potential. And therefore, in the Coulomb gauge, the scalar potential is simply the Coulomb potential of our charge distribution. So we have a very natural interpretation of the scalar potential in the Coulomb gauge. And there's also a reason why the Coulomb gauge has a very economical method a very economical choice for quantizing our electromagnetic theory. Okay, so just a little comparison. So what we've done here, we grouped the Maxwell equation in terms of longitudinal components and transversal field components. And that is, of course, very different to what is usually done if one is interested in relativistic formulations. So where we define the field strength tensor in terms of the four potential that comprises the scalar potential and the vector potential. And we group it in terms of homogeneous and inhomogeneous equations. And that is not what we are interested here, just as a little comparison. All right, so let's look at conserved quantities of our theory. So first of all, one can show that we have three conserved quantities here in particular. So that is the energy, that is the linear momentum, and also the angular momentum. And what happens if we decompose now that also with respect to the different components of the field that are contributing to the energy? So we have the particle contribution, the kinetic energy, and we also have the energy due to the electromagnetic field. Now we can decompose this part in terms of what is due to the longitudinal components and what is due to the transversal components. And if we do that, then we see that the longitudinal component gives us exactly Coulomb self-energy and Coulomb interaction energies. So in particular, the Coulomb self-energies need to be regularized and will contribute to Lamp shifts later on, as one can show. And this is just the Coulomb interaction energy. And what one can also show later on that we will see in more detail is that the energy is identical to the, or other said differently, that the Hamiltonian in the Coulomb gauge is the energy operator corresponding to this expression. So that means that not in every gauge, the Hamiltonian gives us the energy of the system, and that can be also related to that the Hamiltonian is not unitarily equivalent by doing a canonical transformation or gauge transformation. And so only this Coulomb gauge has a very, very special interpretation in terms of the Hamiltonian and the energy. Okay, we can also do the similar thing with the field moment or with the total momentum, and we have the particle momenta added with the field momenta. And so this seems familiar, of course, to some of you, that this is related to the Poynting vector that gives us the total field momentum. And we can also do a decomposition as before, where we just define the longitudinal field contribution to the total momentum and the perpendicular one. And if we do this, again, for the longitudinal component, we get the sum over the charge, the electric charges of our particles times the transverse electric field at the particle position. And if we rewrite this, so we then rewrite the total momentum, and we define these expressions, and we will see later that, or they seem also familiar to some of you maybe perhaps. So we will see later that this is exactly the canonical conjugate to the position operator of the particles in the Coulomb gauge. And therefore we have another nice relation in the Coulomb gauge. Okay, so let us recap a little bit what we saw before. So we started with Maxwell's equation. We had the electric field, magnetic field, the charge position, and the charge velocities in order to fully describe our system at it and its dynamical evolution. Now, after we done this decomposition in terms of longitudinal and perpendicular components, we realized that only the transverse electric and the transverse magnetic field are truly dynamical, because in particular in the Coulomb gauge, we can write the electric field in terms of the charge densities, and therefore they are already accounted for by this Now, our next question is now, how do we quantize this theory? So what we want to get now is we want the Lagrangian and eventually the Hamiltonian after Legendre transformation. And we will also need, of course, in that process, need to identify the canonical variables and their canonical commutation relations. And this will also then allow us to understand the relation between different representations that perhaps are can be expressed in terms of changing the Lagrangian, but they are more general transformations that do not correspond to changes in the Lagrangian. And in particular now, again, we want to quantize in the Coulomb gauge, and for the reasons that I presented before, the Coulomb gauge is a very economical choice in doing so. All right. So remember what we had? So we started with Maxwell's equation that were first order. Now what we know is that usually Euler-Lagrange equation are second order. What we also know after expressing Maxwell's equation in terms of the scalar and the vector potential is this form. And therefore it seems very natural to us that if we want to start from a Lagrangian picture, that we do not start with electric and magnetic field, but with the vector and the scalar potential. And therefore our new dynamical variables will be for the field part of the system will be the vector potential and their time derivatives. Okay, so I just postulate here now that the appropriate Lagrangian is of the following form. We have the particle contribution, and we have the field contribution, and we have some interaction Lagrangian that is responsible for the interaction of light and matter. And we can write it in this form, but this is nothing else than the minimal coupling prescription that we're usually working with, just expressed already in the form and knowing that we have point particles, point charges as our description of matter. And then we can find the Euler-Lagrange equation just to check that we are doing everything right. And we will work here in Fourier space for simplicity, for convenience. So first of all, the Euler-Lagrange equation with respect to the scalar potential. The first observation that one does is that if we go back here, we will find that there is no dependence on the time derivative of the scalar potential. And that means that there is no canonically conjugate variable with respect to the scalar potential. And this is another way of saying that, as we saw earlier, that U is a non-dynamical degree of freedom. And we can see that with the Euler-Lagrange equation, that this expression in the Fourier space with respect to the scalar potential and the vector potential is just the Gauss law. And this will allow us then to neglect or to get rid of the scalar potential by writing it in terms of all the other degrees of freedom. Now we can do the same with the vector potential. We find the Euler-Lagrange equation that is just one of Maxwell's equations. We can also then go back to what is the equation of motion for the longitudinal component of A, of the vector potential. And what we see is that it's just charge conservation. And what this tells us that the parallel component of the vector potential can take any value. And this is related to the fact that by gauge choice, we can find any value we want for that. And therefore, in the Coulomb gauge, as we will see, we make a particularly easy choice for the parallel component of the vector potential. Okay, so now that we studied the Lagrangian and also the Euler-Lagrange equation, we are sure that it gives us at least some of the Maxwell's equations. Let's look at the properties of this Lagrangian. So when we are just in the non-relativistic description of particles, which we usually are when we're describing atoms, then the full Lagrangian is not relativistically invariant. In particular, this expression is just a low velocity limit of the relativistic expression. And so the question arises then, why don't we quantize this expression in terms of what is usually done when we're working with the non-relativistic particle description? So first of all, there is no relativistic quantum theory where we have a fixed number of particles. And instead, what you would do is, in quantum field theory, you start either maybe from a Klein-Gordon or Dirac field, and the excitations of the field are then corresponding to the particles, which are of course indeterminate in number. What we will do is in lecture 3 is that we will see that our non-relativistic Lagrangian that we work with today is the low energy limit of a relativistic quantum electrodynamical description. Okay, so secondly, as a property of the Lagrangian is that, so what we first know is that the Maxwell-Lorentz theory, so Maxwell's equation and Lorentz force, is manifestly gauge invariant just because we write it in terms of the electric and the magnetic field. So if we look now at the Lagrangian, again, we know that we can transform in terms of the vector and scalar potential to new expressions by use of a scalar function. What it changes in Lagrangian is of the following form. It changes, so we can write it in this form, as the divergence of a field. And if we integrate, so this is the Lagrangian density, I should say. And if we integrate over whole space in order to get the Lagrangian, this is just a surface integral, which by definition, one always assumes to be vanishing at infinity, and therefore this part will vanish. Now we will also get a time derivative of a scalar field, and this is if you look at the action, that is the time integration over the Lagrangian, this will give us just some constant function, or some constant correction to the action, which will also not change the equation of motions. However, the equation of motions can be changed by this more general term. But as we saw at the very beginning of this seminar was that this is nothing else than charge conservation. So what it means is that under gauge transformation of this form, the equations of motion of the Lagrangian are exactly equivalent to the old Lagrangian if we accept that we have charge conservation. And therefore, it is necessary if we want gauge invariance in our theory. Now, let's look back again at how many degrees of freedom we have and what our degrees of freedom are. So in the beginning, we showed that if we work with the electric field and in the magnetic field, and we decompose it in terms of longitudinal and transverse components, then we get algebraic constraints with Gauss law and so forth. And we end up with just 4 degrees of freedom, which are just the transverse fields in the field degrees of freedom. Now, similarly, if we work in the Lagrangian with the scalar and the vector potential and also its time derivatives, we saw that we will find constraints for U just because there is no canonical momentum to U, and therefore U is not a dynamical variable. We can find after this that there are only 6 degrees of freedom, which correspond to the vector field, vector potential. What we also know is that we still have a choice of gauge to do in order to reduce degrees of freedom even further. And for that, we saw that in particular, a gauge choice fixes the longitudinal component of the vector potential. And if we do so, we end up with just 4 degrees of freedom. And so in particular, in the Coulomb gauge quantization, we end up with the lowest possible number of degrees of freedom. Therefore, it is a very simple representation to quantize. So let's look back at the Coulomb and the Coulomb gauge choice. So first of all, we saw that U is non-dynamical and can be expressed in terms of the charge current and the vector potential. What we further choose now in due to the Coulomb gauge is that the divergence of A is 0. That means that the longitudinal component of A is 0. And we can write now our Lagrangian, our non-relativistic Lagrangian in the particles in the following form. So we have the Coulomb gauge, which comes from the scalar potential, and we have now the remaining contribution in terms of the vector potential solely, and also the minimum, what is remaining of the minimal coupling interaction of the vector potential with the charge currents. Are there any questions so far? Okay, so now we want to find the Hamiltonian in the Coulomb gauge. So first of all, what we do is we find it for the particles. So again, the canonical momentum to a variable is defined in the following form by the variation of the Lagrangian with respect to time derivative of that variable. And we find for the particles, it's just the particle momenta plus the charge of each particle and the vector potential evaluated at that position of the particle. Similarly for the field, so that means for the canonical momentum to A, we find that this is just a time derivative of A. And this means in the Coulomb gauge now, this is corresponding to our electric field. So that after Legendre transformation now, we can find the classical Hamiltonian in terms of the canonical momenta. So we have this expression, which I showed you from the expression for the energy in the classical case as well, which now we see in the Coulomb gauge has the same form. We have the Coulomb potential, and we have the field degrees of freedom, which contribute to the Hamiltonian. Of course, what we could do now is also we could do the relativistic prescription of that. But as I said, we are interested now here in the non-relativistic limit of the particle velocities. And we will just work with what is known as the usual minimal coupling Hamiltonian for a set of particles. The question now is, what are the physical variables? So first of all, it is not the canonical momentum to the particle position, but the mechanical momentum, which is pi minus QA. So that would corresponds to this expression here. It is the total electric field, which is the transverse component, which is simply the canonical momentum to A, plus the longitudinal component, which is simply the electric field generated by the charge, by the Coulomb charge, by the Coulomb interaction between the charges, and of course is the magnetic field. Now we can do canonical quantization, and in Fourier space in particular, we find then the canonical commutation relation between components of A and the components of the Fourier transform of pi. Of course, we also have that for the particle and its canonical conjugate. So these are just standard expressions. But what we need to be aware of now is that the components of A, of the vector potential, are not independent due to our choice of gauge. So remember, that was the divergence of A is 0. And therefore, in real space, we will not have what we usually would see for canonical commutation relations. So it's not just IH, Kronecker delta, Dirac delta, but it's something else. And we want to see now what exactly it is. So the correct field commutator, what we can do here now is we decompose the vector potential and also its canonical momentum in the Fourier space with respect to the two transversal directions, transversal with respect to the propagation of the field, vector field vector wave components of the vector field. Now, the two transversal components and also the wave vector k form a basis, and therefore we can find a really nice relation. And this allows us then to write in Fourier space as the commutator between A and pi in this form. Now, if we go back to real space and we make use of the property that the canonical momentum is Hermitian, we find this relation. And therefore, we have not any longer the Kronecker delta times the Dirac delta, but we have this, what is known as the transverse delta function, right? And so this transverse delta function has the usual term here, but it also picks out the longitudinal components. So this is the normalized wave vector k in I and j direction, and removes these from our canonical commutation relation. And that is important since we have that in electromagnetism quite commonly. So now a couple of remarks about the Coulomb gauges, that all our dynamical variables are now independent. So that means we eliminated all of the other variables to a minimum. We only have 4 degrees of freedom now, and the quantization can be done in a very straightforward way. There are other choices, of course, and we will discuss this in a little bit. The second one I mentioned before as well. So we separated the field in terms of longitudinal and scalar components with Gauge, which both have instantaneous terms. Of course, for low velocities, it's a very good approximation, which isolates the Coulomb interaction between the charged particles. And because of its simplicity, this artificial separation has its advantages. And a couple of more remarks. So it is not manifestly covariant if we express it in terms of the vector and the scalar potential, just because we break the symmetry of the 4-vector potential, since we eliminated the scalar potential and also the longitudinal component of A. Of course, it's still relativistically invariant if we also take into account the relativistic description of the particles. So this manifest covariance might be needed, however, if we do renormalization, and there we need to eliminate infinities. And therefore, for these purposes, one needs to find another Lagrangian that has more degrees of freedom, more than the 4 that we considered here. And since we have more degrees of freedom, we also need to impose more constraints. And this will allow us then to define a physical state space in this larger dimensional Hilbert space. And lastly, this description of interaction between particle and light can only be valid if we consider the field modes of the electromagnetic field that are in energy below the rest energy of the particles that we consider. And this is nothing else than corresponding to the Compton wavelength. So what happens there is that we would have contributions to coming from vacuum polarization, we would have particle creation, and therefore it would no longer be anymore the non-relativistic description of our fixed number of particles. And that tells us then is that we need a UV cutoff. And I will explain a little bit what the implications of a UV cutoff are. But first of all, let us, now that we have the canonical commutation relations and the operators, let us define creation and annihilation operators as usual, which as always have the canonical commutation relations, and we can then expand our electric field and the magnetic and the vector potential, of course, as well as the magnetic field, which are all transverse in our description in the Coulomb gauge in the following form, where we have the mode functions and the corresponding with the creation and annihilation operators. Now, of course, only since we are working in the Coulomb gauge, we have this nice identification that that the electric field degrees of freedom that we're considering is transversal. So now what we finally achieved is that we arrive at the minimal coupling Hamiltonian, the quantized minimal coupling Hamiltonian in the Coulomb gauge. So we have the mechanical momentum, that comprises of canonical momentum minus the QA term. We have the Coulombic self-energies, and we have the Coulombic interaction energies that come from the longitudinal component of the electric field. So the longitudinal component of the electric field generates, again, for us, the Coulombic energies. And the remaining field degrees of freedom are just what we know as the infinite sum over the harmonic oscillator modes. Okay, so let us look at, in particular, at the interaction terms. So we can split this Hamiltonian in the following form. We have just the particle content of the canonical momentum and the Coulomb interaction. We have the radiation contribution, which corresponds, in general, this is an integral and not a sum, depending if we have discrete or continuum of modes. And we have the interaction term, which is p dot a or pi dot a and the a squared term. Now, what often is done is that people neglect this a squared term, and a simple at the back of the envelope calculation we can have here is, so we want to see what is the ratio of this term to this term. Of course, this is now very classically written. So this is approximately q squared a squared over m, and here we have just q a p over m. We can rewrite this in a little bit, and this is something like the p dot a term over the particle content. And so this term really can only be neglected for very low field frequencies in A. And this will be discussed more in the next lecture. But just so you have a back of the envelope idea of the ratio here. Okay, so let's also talk about the cutoff that is very frequently omitted to discuss, that is frequently not so much discussed in much detail. So first of all, what we need to know is that the Hamiltonian, again, only holds for non-relativistic modes of our field, and therefore we need to be well below the Compton wavelength. So here we have the frequencies, and in this direction we have the wavelength. And at the Compton wavelength, so corresponding to the rest energy of the particles, we need to be on the left side of that. Now, if we include a cutoff in the field, and we realize that the vector potential that the Coulomb gauge comes from the longitudinal component of the electric field, we will also need to include a cutoff in the Coulomb interaction. Now, this cutoff is essentially not needed if we have in our system of particles the distance between those particles much larger than the Coulomb wavelength. And this is, for instance, given if we're considering a hydrogen where the mean distance between the particles, something like that, is of the order of the Bohr radius. And so we're here for a hydrogen atom, which is well left of the Compton wavelength. And so we effectively can neglect the cutoff and the Coulomb interaction. Now, what is often also done is that we include a long wavelength approximation to have a multipolar expansion in terms of dipoles, quadrupoles, and so forth. And so we can also define this point here, which corresponds approximately to ionization energies. So this is alpha is the fine structure constant. So by approximately 4 orders of magnitude smaller than the rest energy or the Coulomb at the Compton wavelength, and therefore usually the long wavelength approximation to have the dipole approximation, for instance, is valid for wavelength or frequencies over here. And so especially in the hydrogen, we have this nice separation of where's the ionization energy, where is the frequencies corresponding to the Bohr radius, and where the Compton wavelength is. Okay. So let's talk also now about equivalent formulations of electromagnetism. So we worked with the Lagrangian, and let's have now a very simple example. So we say we have a Lagrangian that just depends on x as some maybe generalized coordinate and its time derivative. Now we can very easily find the canonical momentum to x with respect to Lagrangian L, and just the usual form. Of course, what you can also do is you find a new Lagrangian, and as we discussed before, a time derivative of a scalar field yields the same equations of motion, and we can therefore regard it as equivalent. So what now is, however, the canonical momentum. So we want to find the canonical momentum with respect to the Lagrangian L prime, and by definition it is just this. And we can also write this then in terms of the old Lagrangian, and this is just the old canonical momentum plus some correction term that is the derivative of f with respect to the generalized coordinate. And therefore what it tells us now is that we have the same equation of motions, but we can describe the system in terms of different variables, different degrees of freedom, and here in particular in terms of different values of the conjugate momentum. And this is some freedom that we have. So if we now want to define what a physical variable is, something that we can measure in the lab, that here just depends on x and x dot, then we say that the observable in the representation corresponding to the first Lagrangian and the generalized coordinate and the first canonical momentum to x must be the same as the observable in the second Lagrangian picture, where we have now as well the same old generalized coordinate, but our new canonical momentum. Now we can apply this definition to our Hamiltonian. So we want to see if the Hamiltonian in the new description with the new canonical variable is the same as in the old. So we just have the usual Legendre transformation. You write it all in the old Lagrangian. And what we find is that it is equal to the old Lagrangian, but what we have here now is a correction term. So therefore, only if this correction term is not time dependent, both Hamiltonians are the same. And this goes back to what I told you earlier about that the Hamiltonian does not need to be the same as the energy operator. And therefore, for instance, when we looked at the Coulomb Gauge Hamiltonian, then corresponded only to the energy operator, but not in general. So that was classical so far. Let us do the same now in the quantum scenario. So we want to find quantum operators in both representations for all degrees of freedom. So first of all, we have the x operator and the p operator. These are satisfy the canonical commutation relations. And then in the first Lagrangian, we can easily identify the generalized coordinate with our quantum with the usual x operator, and also the canonical momentum to x with the usual p operator. And similarly, what we can also do in the new Lagrangian is the same thing. So here, the x, which in both representation, the x is equal, corresponded to the usual position operator. But now we have a different representation for the p operator in terms of the new canonical momentum. And therefore, it is clear now that a physical observable in the first representation does not equal the physical observable in the second representation. So we want to find now just a relation between these two physical variables in order to say how a physical variable should behave under changes of representations. So in order to find this, we find the correspondence. So what we now do is we want to find the representation of the canonical momentum of the second Lagrangian, but with respect to the first representation. And by our here it is, by our relation here, we can write this then in terms of the first canonical conjugate in the first representation, which just corresponds to P, plus this correction term. And similarly, we can also do this for the second, in the second representation for the canonical momentum with respect of the first Lagrangian. And here is just the minus that comes from rearranging, and therefore is the usual P operator minus this correction term. So let us summarize this now. In representation 1, we have the generalized coordinates quantized corresponding to the usual X operator. We have the canonical conjugate to that as the usual P operator. But now we have the representation in the first theory of the second canonical operator now in this form. And similarly, we can write this in the second representation. So what we can learn from that is now that to go from representation 1 or to representation 2 or vice versa, we can apply this unitary transformation that is generated by F, our change in the Lagrangian that just depends on X. And this unitarily transforms between these two representations. So now that gives us the means to find the relation between physical observables in different representations. So that means the physical observable in the first representation with X and P corresponds to the second representation of the physical variable, but now with a changed canonical conjugate that depends on this generator of the unitary transformation. We can again apply this to the Hamiltonian picture and look how the Hamiltonian relates. Again, we have the canonical conjugation of the Hamiltonian from the old to the new picture, and we have this time derivative of the generator. And therefore, generally, they are not unitarily equivalent in the quantum case either. And similarly, then, we can do this for the state vectors. So they transform also by this unitary operator generated by F. Now, we want to go a bit more general. So we want to look at operators that not just depend on the generalized coordinates and their quantized observables, but also if you have a dependence on the generalized coordinates, the generalized momenta for particles and for the fields, and also in general in explicit time dependence. So what stays the same is that the field, the states of the system and the observables of the system transform in the usual way. But what is different now is, since we have a dependence on the canonical momenta in a generator, that T is not equivalent to a change in the Lagrangian. So it means that there are changes in the representations which cannot be represented by a change in the Lagrangian. And what is more is that in general, X no longer represents the particle position in a new representation. So what we had in this case is that the particle position was always represented by the usual X operator. But this is no longer true if we have more general transformations. And another point is, of course, it's important if you want to find physical predictions that we transform them in a coherent way. So we have the inner product of two states in one representation, where we also have in general some time evolution from T0 to T. They have to be in relation to the old inner product in the old representation. And that needs to be coherently done in order to have physically reliable predictions. Now, it's important to notice that gauge transformations are then just a subset of canonical transformations, which are more general. So in general, we have unitary transformation, and there are some gauge transformations that allow us to go to different gauges. We will see in the next lecture that there are, for instance, in the two particle case, we cannot go to a different representation of the usual multipolar expansion from the minimal coupling Hamiltonian with a gauge transformation. And for instance, there are even more general relations. So for instance, there is no unitary transformation from the Coulomb gauge minimal coupling Hamiltonian that I presented before in order to go to the covariant quantization, what we do in lecture 3, just because it is related to a different state space. So since we don't have the same state space of the Coulomb gauge quantization and the covariant quantization, we cannot just do a unitary transformation to find those. Okay, so let me wrap up here. What we saw was that we can very easily, by separating the fields in terms of longitudinal and transverse field components, find a very easy and simplified description of the light-matter interaction. So in particular, we reduce the field degrees of freedom to just 4, which is the minimum possible by simply eliminating the vector, the scalar potential and the longitudinal component of the vector potential. What we then did was we quantized in the Coulomb gauge very easily, very straightforward, just because of the very simple form of our Lagrangian. And this allowed us to go by Legendre transformation to the minimal coupling Hamiltonian. Now, we also saw how we can go to different gauge different representations of this Hamiltonian, but we didn't see any explicit examples so far. So next week, we want to see explicit examples of this different representation of the light-matter interactions when describing in particular a bound system of particles, i.e. atoms. And we also want to then, in this context, derive the multipolar Hamiltonian when we consider all quantum degrees of freedom of the atom. And this will result in some interesting phenomenology that we want to discuss in more detail. And so with that, I want to conclude and invite you to ask questions if you have any.
All right, thank you, Richard. Thank you for the talk. Very nice seminar. Okay, questions. I noticed that there were some people from the department joining. Apparently, they didn't get the link. Richard, we need to fix that. You need to tell the link.
There was an email.
Yeah, but the email, some of the people said that the email didn't contain the link for some reason. Anyway, let's make sure that the seminars are announced. Some people arrived very late and then they left. So for the next ones. Anyway, questions from the audience. No questions? Well, I guess everybody followed. I mean, the people who come, most of the audience are from the group. And I understand if there are not that many questions. It was very thorough. Okay, nobody has any questions. Well, in that case, we'll thank Richard again. Thank you, Richard. Very nice seminar. Next week, probably we'll have some people from outside the group too. All right, I'm going to stop the recording now.